Welcome back, Falcons. We are into chapter 20, if you can believe it. And this is one of those pivot points in our class and really the crux of most of the statistical work that statisticians do. And this goes to the idea of testing hypotheses. And just like testing hypotheses in a science class, in most other social sciences, you want to actually find something out. And so we have to ask questions. We go about collecting data and we see, is this statistically significant? And so the magic that we've been looking at with sampling distributions, or then looking at a point estimate and looking at the confidence interval to try to find the true population proportion, all of that work previously from chapter 18 and 19 is to build up to be able to make these hypotheses statements and do this process. This really is the scientific method at work. And so, of course, we have our homework problems. A large portion of this we are going to do together because I want you to get good at this method. And it takes time to actually write out all of the steps for these. So we're going to see some things that are not just from the notes, but I'll make a new document and we'll actually do the full process of what the AP and what I expect you guys to be able to write. So again, we start with our objectives. We say we're going to test a null and alternate hypothesis about population proportions. And note, I'm focusing on proportions for the rest of Unit 5. We will see means, so quantitative data, in chapters 23, 24, and 25. So that we'll do the exact same work that we're doing with testing hypotheses and building confidence intervals with means. But for now, let's keep it simple, proportions. And when I say proportions, I mean, let's talk about categorical data. Okay, so we're testing null and alternate hypotheses. Okay, so then what is a hypothesis? Now you know you have some basic understanding of what a hypothesis is because that's what we've done in science classes, biology. Write out your hypothesis, write out your thesis statement. So hypotheses are models that we adopt or believe and against which we test some actual results. If our results do not support our assumed hypothesis, we are then forced to modify the hypothesis. This is kind of, in a math class, you might have seen like proof by contradiction oftentimes. We're going to hypothesize something happens, or like there's a base case. We call that the null hypothesis, or our initial assumed hypothesis is our null hypothesis. Like when you see null or initial hypothesis, this is H naught or H sub 0. We just say H for hypothesis, and that's our initial hypothesis, or our null hypothesis. Our null specifies a population parameter, so we're making a statement about P and proposes a value for that parameter. So we're saying the population parameter is something. So the opinions of the students at Divine Child on block scheduling is 40% in support. So we'll usually write the null hypothesis in the form H naught, or the null, and then we'll put a semicolon and write the parameter. Oftentimes it's going to be P equals whatever the proportion value is. Now, the alternate hypothesis, also indicated as either H sub A or H1, depending on what textbook you're looking, includes the values that are not included in the null hypothesis. Okay, so more so just on our base case and then what's the alternate. The null hypothesis specifies a population parameter for the variable of interest and supplies a value for the parameter. Sound familiar? So let's do this with an example. Let's assume that Alvin Big Monk So tells us he makes 80% of the putts he takes. Okay, let's say we're at a putt-putt golf place. Maybe we are allowed to go and see each other in this situation. If we're to test his claim, we will test it against the 80% that he claims is his true putting percentage. So we would say our null hypothesis is that P naught equals 0.8. So the alternate is that our alternate hypothesis would be that he doesn't make 80% of his putts. So we start by assuming the claim is true. That's what we mean by a hypothesis. The alternate assumption is that the claim is false or not true. And then we go out, we collect data by having Alvin shoot many, many shots. And then we calculate the proportion of made putts out of the many putts. That would be our sample proportion. We then ask, how likely is it to get the results that we found given that his initial statement was true? So given if the null hypothesis was true. I'm hoping that this starts sounding familiar because it's a lot of the pieces that we've talked about. So the beauty of statistical tests is that we can quantify our level of doubt. We use the model proposed by the hypothesis to calculate the probability that the events we observed could happen, provided that the null hypothesis, the thing that we was originally claimed, is true. And so this p-value that we're talking about, that is the probability we're looking for, the probability that quantifies exactly how likely we are to see the results that we got if the null hypothesis is true. So this is a conditional probability, and that's what we call the p-value. So this conditional probability is the probability we get our sample proportion given our true proportion is true, that it is that case. We've talked about conditional probability. The last time we've seen that was probably in chapter 15. Remember, probability of B given A is true is the probability of A and B divided by the probability of A. You should know that. So a value, alpha, this is alpha, not just A, is determined a priori, or before you begin. Sounds familiar, kind of like confidence level. This is the value we use to establish what is sufficient to convince us the hypothesis may not be true. So what probability would be small enough to convince you that the data that we found is unlikely? And this is what we call the alpha level. Hence, we use alpha. So when the data are sufficiently consistent with the model, in other words, not significantly different from the null hypothesis, the calculated p-value, or the conditional probability that we got our data given that the null hypothesis is true, is relatively high. The chances that we get the thing if we assume that this was true is pretty high. And we failed to reject the null hypothesis. We didn't find any evidence that disputed Alvin's original claim. So in that case, we have insufficient reason to reject the null model, or to say that Alvin's 80% putt making putts is false. We never claim that to have proven our null hypothesis. Instead, we say we fail to reject the null when the data are not significantly inconsistent with our model. The variation from the model that we observed is attributed to sampling variability. Hence why we're using the sampling distribution and all of those techniques, is because from sample to sample, we're going to get some sort of variation. It should. And so the sampling variability, or chance, and cannot be claimed incompatible with our model. So if the p-value is low enough, so what does it mean by low enough? Well, if the p-value is smaller than that original alpha that we set out, that convincing number that we would say, this is pretty unusual, we reject the null hypothesis. So our original statement was false. That's what we mean by reject the null hypothesis. And conclude that we observed what we would have observed would be extremely unlikely if the null hypothesis was true, thus incompatible with our model. I know this is going to sound confusing to begin with, but really, statistically, we will either reject the null or we will fail to reject our null hypothesis, our original statement. We never declare the null hypothesis to be true or proven. Remember, there's no exactness when it comes to statistics. We have to use these types of squishy words. There's always some level of uncertainty when we involve probabilities, because we do not really know whether it is true or is not true. We simply don't have enough evidence to reject the claim. So to summarize, this process, big picture-wise, we establish a value for the parameter based on some model. let's say our null hypothesis. So we say our null hypothesis is 80% made putts. We establish an alpha value against which we are going to compare a p-value. This alpha level is how unusual do we want this data to be? And it ranges. Maybe you want to be below 10%. Maybe you want to be below 5% probability. Maybe you want to be below 1% probability. So calculating observations, we calculate a test statistic. This test statistic will be our sample proportion. And then we're comparing that sample proportion to how likely would we be able to get this? How far away from our assumed null are we? The p-value is the probability of obtaining the test statistic if the null hypothesis was true. So we went out and collected this data. We assumed we were at some sort of initial position. And if all of the conditions that we will go over are met, let's say we got a sample proportion here. What we can do when we say the p-value is calculate the area under the curve, or how likely it is to be that far away from our assumed position. If the p-value is very small, less than the alpha that we selected, we reject the null. If the p-value is large, or if it's greater than our alpha level, we fail to reject the null. So those are our two options. So the process that we're going to conduct, and this is much better done with a problem set. There are 4 basic parts to a hypothesis test. You have your hypothesis, you have your model, you have the mechanics, which is really doing the work, and then you have your conclusion. So we're going to look at these parts, and then I'll give you another mnemonic to help you remember the process.